Solving equations is an essential skill in calculus, so we will go through the various types of equations and use the skills that we've recently developed in order to actually solve them. Let's first discuss what is really an equation and what does it mean to solve one. So here's an example of a very simple equation: x plus 3 is equal to 2. So as opposed to expressions, which is what we dealt with in the previous sections, where there was only one side to it, and we were the ones that continued on with simplifying and writing equals and continuing with the expression, an equation has two sides that are connected by an equal sign, and therefore must in fact be equal. So to look for a solution means to look for the values of the unknowns in the equation, in this case x, that actually make this equation true. So what value of x in this case So what value of x in this case will actually make this equal, make this expression true? Well, in this case, it's not a very difficult equation, so I can simply guess and check and see that in this case, x should be -1, because -1 plus 3 will in fact give us the value of 2. So this is important to remember. We're looking for something that will actually make the original equation work. With different types of equations, we will employ different types of techniques. Let's start with linear equations. Linear equations mean degree 1 equations, and we will later see that they're called linear because their graphs are actually lines. Degree 1 refers to the degree of the unknowns. So we're not going to see here any x squares, we're not going to see any square roots or any other powers of x except for power 1. The one method to use with these equations is to simply isolate the variable. Okay, so we're going to try to get the variable all by itself on one side, and that will allow us to solve the linear equation. So let's see how this works in the first case here. 3x plus 9 is equal to 17. If I'm going to try to isolate the x, I have to first of all get rid of this plus 9. We can move it over to the right-hand side, or you can think about that as subtracting 9 from both sides, which will then give us 17 minus 9 on the right and simply 3x on the left. So notice that here I'm not continuing to write equals equals. Whatever happens when I modify the equation, I'm going to get another equation, preferably similar to the one before. Okay, so here I can actually perform the subtraction. 17 minus 9 is 8, but I am not interested in the value of 3x. I would like to know what x is. So my next step will be to divide both sides by 3. And this is important to remember too. Whatever you do to an equation, you must do to both sides of it, because I have to keep the equal sign true to itself. So I cannot just divide the left-hand side by 3 but not the right-hand side, because then these two things will no longer be equal. Okay, so dividing both sides by 3 will give me that x is equal to 8/3, and that is therefore the solution to the original equation. You can plug it back in to make sure that it actually works out, and you will see that it does. Take a look at this slightly more complicated looking linear equation. I can see that it's still linear because the only times that x's occur, they do appear to the power of 1. Now, as opposed to here where the term containing x was just one term by itself, here I have x's inside the various brackets. So in my first step, I'm going to open up these brackets and open them up carefully. Make sure you multiply through by everything to get this. Now, my final goal is to isolate x, and so have it on one side by itself. But here I have x's on both sides, okay? So let's say I decide, and you will get more comfortable with moving things around or subtracting from both sides as you practice more. It doesn't matter what side you isolate x on. I'm going to pick the right-hand side here, because if I subtract 2x from both sides, subtracting it from the right will keep the coefficient in front of x positive. Okay, so the first thing I'm going to do here is subtract 2x from both sides, which will then make it disappear from the left. I can, of course, see that this is now just x. So let me do similar terms here. And in my next step, I'm going to get rid of this 3 by subtracting that from both sides, which will then yield x equals 5. And this is then my final solution to the equation. And again, I can plug it back in just to double check and see whether or not this actually works out. Okay? This is linear equations. Linear equations are fairly straightforward. The next degree up will be quadratic equations. So this is then degree 2 equations. Anytime you see x appearing to the power of 2 or below, so you should still be able to see some factors that are in fact linear, but the equation degree is determined by the highest power that you see in the equation. For degree 2 equations, these guys can have 0, 1, or 2 solutions. And this is important to remember. I think some people get stuck on the fact that there will be equations of any type, they will have no solutions at all. Remember that not all problems in life have solutions, and not all equations in math have solutions. So having no solutions to an equation is a perfectly acceptable situation. There are a number of ways that you can approach quadratic equations. You can try to factor it. This might work very well if the equation has nice roots and nice numbers, but if that fails, you can always use quadratic formula, and we will see how that works in a second too. So for those of you who don't remember what the formula looks like, here it is. If I have a quadratic equation, ax squared plus bx plus c, where a, b, and c are coefficients, then the solutions, there are potentially 2 solutions. I'm going to call them x1 and x2. And they are actually, we have a formula where we can compute the solutions or roots or zeros is what they're also called, based on the coefficients of the equation. So the quadratic formula says it's minus b plus or minus square root of b squared minus 4ac all over 2a. Okay? And as you're using this formula, you will actually be able to witness either of the 3 situations. If the thing under the square root turns out to be negative, that's not possible, which means that the equation will have no solutions. If this entire square root turns out to be 0, that means that adding and subtracting it will yield the same number, which means the equation will then have 1 solution. But if this square root is something you can compute and it's an actual number, then that's not 0, then this is when you're going to encounter 2 solutions situation. Okay, so let's take a look at the variety of quadratic equations and see what methods we can use and how they will work. Once again, trying to factor is probably going to be your first go-to method to see, because that will probably be the fastest way to approach it. So let's take a look here. This is a quadratic equation because the highest degree I see is 2. So I'm going to try to factor it first of all. So I'm going to think of 2 numbers that when multiplied give me 2 and when added give me a negative 3. Okay, the numbers are pretty nice and small, so it doesn't take very long to figure out that what I have is x minus 1 and x minus 2. This is me simply factoring the quadratic on the left, but I still have this equation that says that my whole quadratic has to equal to 0. So I have to inherit that together with my next line. Okay? And this is where you see the real power of factoring in solving the equations. What I have here is a product of 2 things. And the product of 2 things, I am told, is equal to 0. Just take a step back for a minute and try to think, if I ask you to multiply 2 numbers together and get a 0, what can those numbers be? Can you ever multiply 2 non-zero numbers and get a 0? Like 2 times 3, or 2 times a half, or 2 times negative 1, right? You will soon discover that the only way to get 0 as a product is if one of the pieces, one of the factors, was 0 in the first place. And this is why factoring is so useful, is because now this boils down to me saying that either the first bracket is 0 or the second bracket is 0. So I've managed to turn my quadratic equation to break it up into smaller pieces, and now these guys are quite simple to solve. So this will give me x equals 1, and this will give me x equals 2, which are the solutions to the original equation. Okay? This will always work with factoring this way. So as long as we can actually factor whatever equation we have, we will be able to fully find all of its solutions. Let's take a look at this quadratic here. So here, one of the immediate issues is the fact that what I have up in the front is 2. This factoring method works really nicely if the coefficient in front of the x squared is 1. Many of you also would have seen methods that will allow you to think of the two numbers similar to the way we did here when the coefficient is not 1, but that method is a little bit more involved. So this is already a pretty good cue to the fact that it's probably faster and safer to simply go straight for the quadratic formula. Okay, so using the quadratic formula for this expression will mean that I am looking for two solutions, and notice where my a, b, and c occurs. So my a is 2, my b is -8, and my c here is 3. So be careful about that. You are inheriting the coefficients together with their sign, be it positive or -1. And then following through the formula, plugging everything we have in, we're going to have -b, so -8 will give me 8, plus or minus the square root of b squared minus 8 squared is 64, minus 4 times a, which is 2, times c, which is 3, all over 2 times a, which is 2. Okay, and computing this value under the square root, I will get 8 plus or minus, whatever happens under the square root turns out to be 40 divided by 4. Okay, so I have two solutions. X equals 8 plus root 40 divided by 4, and x equals 8 minus root 40 divided by 4. If you would like, you can most definitely compute the decimal approximations of both of these numbers. So for example, if you were to sketch this on the line, it's probably better to know approximately where these numbers lie. But for all the other purposes, these expressions are better because they are exact. What the calculator will give you is an approximation. This is the exact expression. Those are the exact expressions that correspond to the two roots of this equation. Okay, moving along, let's take a look at this equation now. This is back again with the coefficient of 1 in the front, so maybe we can think of two numbers that multiply together to be 5 and add together to be -2. 5 to multiply together to be 5 and be integers, we don't have that many choices. We have 1 and 5 as the factors of 5, so those will have to be the numbers, but no sign combination of them will give me a -2. So if it's not easy to find those factors, we might as well go straight for the quadratic formula. And the quadratic formula in this case will give us -b, so -2, plus 2, plus or minus square root of b squared, -2 squared is 4, minus 4 times a, which is 1, times c, which is 5, all over 2 times a, which is 1. Okay, now notice here then, I'm going to compute what's under the square root, and what am I going to get? 4 minus 20 is -16 over 2. Now, I cannot take square roots of negative numbers. We've discussed that in the exponential section, which means that here, this operation cannot be performed. This does not exist or is undefined, which means that in this case, there are no solutions. All right, let's take a look at this quadratic, which looks a little bit different from the ones that we've considered. Notice that in every other case we've considered, the quadratics here all had 3 terms. So sometimes they're also called trinomials because there's 3 pieces to them. This guy only has 2. So we can proceed in different ways here, and I'm going to do 2 different ones. One way, recall that generally one way to approach solving quadratics is to first of all factor them. Well, I know that this is the difference of squares, and I can factor it using that idea, which will give me x plus 3, x minus 3. And again, remember that this is an equation, so I have to inherit the other side of it as well. And as before, the powerful thing about factoring is the fact that a product is equal to 0 only if one of its factors is 0, which allows me to immediately break down this equation into two smaller ones. So either x plus 3 is 0 or x minus 3 is 0, which immediately gives me that either x is negative 3 or x is 3. And those will be my two solutions. This is how you solve this equation if you decided to proceed by factoring. In this case, because there's only two terms, I mean, of course, you can always apply quadratic formula, okay? So always keep that in the back of your mind. The quadratic formula will work for any quadratic equation whatsoever. It's just in this case, this middle term b has the coefficient of 0, because it's simply not present here at all, okay? But the other way to solve this particular equation would be to try to isolate x. But you're going to have to be very careful when doing that. So the second method is to isolate x. I can add 9 to both sides, so what I'm going to get is x squared equals 9. And then in order for me to solve for actual x, I'm going to take square roots of both sides. I'm going to think of what number squared, right? This is the real question. What number squared equals to 9? Okay, so if I apply square roots to both sides, one thing I have to remember, of course, is the fact that there are two square roots, a positive one and a negative one. So here, square root of 9 itself is 3, so my answer will be plus and minus 3. So this second method, while sort of seemingly shorter than going through the factoring, does have one issue, and that is if you forget the plus and minus in front of the square root sign, then you will lose one of the roots. Factoring is kind of foolproof in this case because there's no way you're just going to forget a bracket, okay? So this method is perfectly appropriate. Just be careful and remember that there are always two roots, a positive one and a negative one. These last two equations on this slide are kind of quadratic types, but not themselves quadratic. Okay, so we notice, of course, that here the highest degree in the equation is 4, so this equation itself is clearly not quadratic. And here I have a square root, which means that this isn't quite of the form of the quadratic equation, where the only things I'm allowed to see are squares, linear terms, and constants in terms of x. Okay, but what does relate these equations to our topic is the fact that they are, as I said, quadratic types. So for example, I noticed that the only x terms that are present here are x to the 4th and x squared. There's no x by itself, and there's also no x cubed. So the only powers that are present of x are even, which means that I can sort of do this kind of interesting substitution on the side where, let's say I introduce another variable, I call it y, and I make it stand for x squared. Because what I notice here really is that I have x squared squared minus 5x squared minus 36 equals 0. So if I actually allow this to be colored in and just sort of like if you squint at it and don't notice that it's x squared in the middle, you notice that this equation in itself is quadratic. So if I allow for this substitution, I can then just replace what's inside by y, and then hopefully we'll see the structure of the equation a little bit better. So y squared minus 5y minus 36 is equal to 0. Okay, and now this looks much more familiar. This is now a quadratic equation in terms of y, and I can apply one of the methods that we've just discussed. So I can think of two numbers that multiply to, or I can first try to think of two numbers that multiply to be minus 36 and add up to be minus 5. Well, minus 36, that's 4 and 9, and if you play around a little bit with the signs, you will quickly see that y plus 4, y minus 9 actually do work. And once again, once you factor, this will get reduced to simply working with two smaller equations. So on this first one, I need that y plus 4 is equal to 0, which will then give me that y is equal to negative 4. And on this right one, y minus 9 has to be 0, which will then mean that y has to equal to 9. Now, my original equation was in terms of x's, which means that my final answer better be in terms of x's as well. So I'm going to use the substitution back and recall that y was actually x squared. So I'm going to plug that back in. This means that x squared has to be negative 4, and this means that x squared has to be 9. Now I need to solve these two equations for x. Let's take a look at this one. X squared is negative 4. No number squared will produce a negative result, which means that this part of the equation produces no solutions. Looking at this right-hand side, though, here, it's the exact same equation that we've seen before. So you can solve it similarly or simply copy down your answer. This will give me two possibilities, x being plus or minus 3. So these are my two solutions to the original equation. Notice that if this left-hand side worked out and also produced two solutions, that would mean that this equation would have had 4 solutions in total, okay? Which is fine because it's not actually quadratic, it's power 4, so we can actually have up to 4 solutions there, okay? This equation is very similar in nature to how we treated the previous ones, except for now I have square roots that play the role of this substitution part. Okay, so once again, if I just notice that the only powers are square root and x, which is its square root squared, then I can rewrite this equation as square root squared, which is x, plus square root minus 6 equals 0. And then I can notice that if I shade this in, and again, sort of squint at it, then this is actually now a quadratic equation in square root of x. So I can perform a substitution, y equals root x, and I'm going to get y squared plus y minus 6 equals 0. This is great news because now this is a quadratic equation in y, and that I know how to do. In fact, this is one of the equations I believe we've just seen recently somewhere. So I can split this up, or I can factor it out, and this will give me y minus 2, y plus 3 equals 0. And once again, factoring sort of to the rescue, because now the product of two things is 0 if one of the things is 0, and I can split this equation up. This side will mean that y is equal to 2, whereas this side will mean that y is equal to negative 3. And then I also have to, just like in the previous example here, realize that I need the answer in terms of my original variable, which is x. So I need to turn these y's back into x's using my substitution. So on the left here, I have that root x is 2. And here, because y is root x, I have that root x is negative 3. Great. So what do I have here? Root x is 2. So notice that there is implied positive sides on both sides. So I'm trying to think of a number so that when I take a square root of it, I get a positive 2. Well, there's only one such number, and that is 4. On this side, I have that square root of something is negative, which of course can never be a thing, which means that this right-hand side produces no solutions. Okay, so the only solution to my original equation, of course, then is x equals to 4. For these types of equations, or anything that actually involves square roots, you should plug in your solutions back into the equation to make sure that they are not what is called extraneous. So they were not introduced somewhere in the middle by applying a squaring of both sides and therefore sort of changing the implied domain of the function. So if I plug 4 back into this equation, I'm going to have 4 plus square root of 2 minus 6 equals 0. And I need to make sure that that works. In this case, it does, which means that this is a true solution. We will see the cases of extraneous solutions where a seemingly fine result doesn't actually work when we plug it back into the equation. So be careful about that. Always double check your solutions with equations that involve square roots or some kind of implied squaring in the process to make sure that they actually work in the original. These other types of equations are everything that we were not able to classify as linear or quadratic. So these are equations that involve square roots, for example, of just x's or actual linear expressions under x's. These are equations of higher degree, like cubed, or even higher degrees like this here. These are equations that have various denominators and square roots appearing in more than one place. Okay, so let's start off by taking a look at this first equation here. The one thing that you can notice right away is the fact that no matter what happens throughout the solution process, the one thing that x most certainly cannot be is 0, because here we will be dividing by square root of x, and square root of 0 is 0. So right away, you can make a little note to yourself that if you do get 0 as one of the potential solutions, it will most certainly be extraneous. In fact, there's even a stronger assumption than you can notice, and that is the fact that x has to be positive, right? We cannot compute square roots of negative numbers, so also right away, you in fact should say to yourself that whatever x turns out to be, it must be greater than 0. Strictly greater than 0, it cannot be 0. Okay, so let's say you've made this note, or maybe you didn't, but we would like to solve this equation. We will check for extraneous solutions anyways, so this might be a shortcut in the beginning, or we'll discover what solutions are extraneous at the end by simply plugging them back in. There are, as with almost any equation, more than one way to proceed. So I will go through one of the possible ways, but please take a look at this equation and think of what would be more natural way for you to proceed. For example, you could move everything to one side and do common denominators. I am going to do what I think will be one of the shorter methods, and that is I'm going to try to get rid of the denominators as soon as possible. Okay, so that there's also a number of ways to do that. We can figure out what is the greatest common denominator and then multiply by that, or in this case, because it's an equation, I can also just cross multiply. So what I will get is that 4 root x is equal to 1 times square root of x cubed. Great. Now I have two sides with without the denominators, so that's looking a lot better, but there are still square roots, and that is not something that I can easily extract x's from. Again, there are more than one way to proceed from this point on. What I'm going to do is take this equation and square both sides. Both sides are guaranteed to be positive, so I'm not losing any information, right? So if one of them was a negative here, you'd have to be a little more careful, but here both sides are positive, so I'm not introducing something that's illegal. So I'm going to square both sides, and remember that when we are squaring, actually let me just rewrite that just to make sure that we are all following all the small steps here. When we're squaring, the square has to come down on everything in the expression. So this will be 16x, and then this will become x cubed here. Okay, once I have that, I'm going to move everything onto one side. So I'm going to subtract 16x from both sides, and I'm going to get x cubed minus 16x equals 0. Once I'm here, I'm going to factor this out. So I can see that I can take out x, and I'm going to have x squared minus 16 left. Here, I know I can factor out even further because x squared minus 16 is a difference of squares. So I'm going to pull out all of my simplification practice, put all of it to use, and actually be able to come up with this simplified expression here. Okay, now once everything is fully factored out, again, remember what we just talked about. A product is only ever zero if one of the factors is itself zero, which means that this allows me immediately to break up this equation into immediate solutions. So this factor of x is 0 when x is 0. This factor is 0 when x is equal to -4. And this last factor is 0 when x is equal to 4. So I have 3 potential solutions here, and now I need to plug them back in or check them against my constraints to make sure that they're not extraneous. We will notice that, of course, x equals 0 does not work because I cannot divide by 0. X equals -4 also does not work because I cannot take square roots of negative numbers. But x equals 4 plugged in will actually yield an equation to be true. So this is my only actual solution here, whereas these guys are going to be extraneous solutions. So notice that this last step is essential in order to not lose information about the equation. Let's next take a look maybe at this example here. So the issue here is that I have 2 square roots. They're on both sides and they're not the same. So I cannot just do some kind of similar terms. I cannot put them together using similar terms. So what I can do, and the way that I've gotten rid of square roots here, is simply to square both sides. Here, again, I can see that both of them are positive, so I'm pretty safe. Checking for extraneous solutions will always keep you safe no matter what. But here, there are a couple of ways to proceed. I can move both square roots onto one side and then square, or I can square it as is. It doesn't actually matter. I don't think any one method is shorter than or significantly shorter than the other. So I'm going to square everything as it stands right now. Okay? And you're going to have to be extremely careful here to not miss something, to not mess something up, to really be squaring it very carefully. So I'm actually going to rewrite the whole thing with the squares on top of it. So I'm squaring the entire left side and the entire right-hand side. So notice here that rewriting this sort of forces me to realize that I cannot simply bring the square down on both of these things because this is a sum, not a product. So I cannot distribute it this way, which means that I will actually have to expand this out. So I'm going to have to write this twice and multiply across all of the terms and FOIL it in. The left-hand side here is much more simple. Square root and square are inverse operations, so they cancel each other out, and I'm going to get 2x minus 1 back. Now, opening up the brackets, either you remember I remember the formula for a plus b all squared, or you actually go through and FOIL everything out. You will notice that square root of x minus 1 times itself will give you x minus 1, and then I'm going to have plus 1 of the roots plus the second one of the roots. So I'm going to have this term 2 times square root of x minus 1, and then plus 1 remaining from 1 multiplying by 1. Okay, excellent. So now the problem here, of course, is I still have a square root, but it's looking up because I used to have 2 square roots and now I only have 1. So this is good news. Please make sure that at this step you take a little second here and think before doing the next operation. Squaring everything will not solve everybody's problems, right? Because if I square this entire side, I'm not squaring the square root by itself, which means I will be introducing sort of these middle terms the way I did here. So what I'm going to do first is isolate this square root on one side and then square it. Okay, it's actually fairly nice here because this one and this one will actually cancel each other out. And so I only need to move this x over to the left. So what am I going to have here? I have 2 x's and this will become a minus x. So on the left, I'm going to have x. And then I'm going to inherit this minus 1 that's never left. And this equals to 2 square root of x minus 1. Great. So I'm going to now square both sides, which will allow me to actually get rid of the square root. So on the left, I'm going to get x minus 1 squared. And here, also be careful, I'm squaring everything. So I have to square the 2 and I have to square the square root. So I'm going to end up with 4 times x minus 1. There is a number of ways to solve this equation. You can expand out all the brackets and move everything to one side and then either try to factor or apply a quadratic formula. Or you actually can notice that, for example, x minus 1 appears on both sides. So I'm going to move everything to one side, but not open up the brackets. Okay? And now I notice that both of these terms have x minus 1 in common. So I can factor out x minus 1. Then from the first term, what I'm going to have left over here, this used to be x minus 1 squared. I took one of the x minus 1's out, so I'm going to have 1 left. And then this was minus 4 times x minus 1. So I'm simply going to have minus 4 left. And it's once again equal to 0. Okay, simplifying this a little bit further, you will notice that, of course, this bracket becomes x minus 5. So this whole thing will become x minus 1, x minus 5 equals 0. And this is, once again, the exact same logic that we've talked about before. A product of two things is 0 if one of them is 0. So this will give me a solution of x equals 1, or it will give me a solution of x equals 5. I have to check both of these to make sure that they actually work or not work in the original equation. Okay, so let's actually go through the substitution. If I plug in x equals 1 into this equation here, what am I going to get? I have square root of 2 minus 1 equals square root of 1 minus 1 plus 1. Is that true? Well, this square root will be square root of 1, which is 1. This will be 0 plus 1. So indeed, 1 is equal to 1, which means that x equals 1 as a solution works and is not extraneous. I have to plug in the second one, which was x equals 5. So plugging this back in, what am I going to get? 2 times 5 is 10 minus 1 is 9. So square root of 9 is equal to square root of 5 minus 1, which is 4, plus 1. Square root of 9 is 3, equals to 2 plus 1, which is also 3. This is excellent news. That means that x equals 5 also works as a solution. So in this case, we don't have any extraneous solution. Every solution that we found actually ended up working out. Great. So going back through this example, please notice that you had to be very careful when squaring to make sure that you don't just get rid of the square root and plop a square on top of the 1. If you are squaring a sum, that means that you're repeating it twice and you actually have to FOIL it all out. Higher degree equations, so this is our next couple of examples here, is equations of the degrees that are not quadratic but higher. So for example, this is cubic and this is higher still. If you look at the highest degrees here, this is x, this will be x squared, and this will be x squared. So if I were to expand this whole thing out, then the total highest degree I'm going to have is going to be degree 5. 1 from here, 2 from here, and 2 from here. But I don't have to expand it out. In fact, I'm going to try to avoid expanding it out at all costs. Because again, remember, having things factored out is exactly what provides me with the most efficient way to split up the equation into pieces and get at its roots. So in fact, I'm going to take a look at the brackets and see if there's any further factoring that I have to do. X minus 2, there's nothing else I can do to simplify this. X plus 3. Nothing still. X squared minus 16, I can do better. I can transform this factor into x plus 4, x minus 4 as per the difference of squares formula. And I'm actually just going to simply copy over the rest of this equation. Okay, once I have this, I can see that my factors are as small as they can possibly be, which means I can apply my very convenient factoring logic. This is all a product of things. A product of things is only ever 0 if one of those things is 0. So I can go through bracket by bracket and look at values of x that make that particular bracket a 0. So I'm going to have x equals 2, x equals -3, x equals -4, and x equals 2, 4. This equation had no square roots, so I'm not worried about anything extraneous, which means that all of these will be solutions to my equation. This is really great news because this was really the least amount of work that I had to do to actually get at the equations, at the solutions of the equation. Let's take a look at this cubic equation here. So it's cubic because the highest degree I can see is 3. And this is here to really highlight one of the things that you should avoid doing in order to make sure that you don't lose any roots. So one thing that is really tempting right at this very first step is to divide both sides by x. You notice that both sides have x, so wouldn't it be very nice to divide by it? The problem with division, of course, is you never want to divide by 0. But if you decide to divide by x, you don't know what x is. So x could potentially be 0, and you right here would be introducing an operation that is illegal. Okay? So never divide equations by unknown quantities, which is what x is. Always factor instead. Okay, so let's see what we need to do. Let's move everything over to one side. So I'm going to have minus 4x on the left now. And once I have this, I can factor out that x. Not divide by it, but factor. Okay, so let me make a quick note here. Do not divide, because you will lose a root, but rather factor instead. Okay, so if we do that, I can factor out x. I'm going to have x squared minus 4 left. And then I can further break down my second bracket into the difference of squares, plus or minus 2. And here I'm going to have solutions x equals 0, x equals -2, and x equals 2. Again, none of these are going to be extraneous. I didn't have any square roots, so these are all of my solutions. So notice that had I divided by x at this point, so let me make a really quick note of what would have happened if I proceeded incorrectly. So if I divided by x here, I would then get x squared equals 4, taking square roots of both sides and not forgetting that I'm going to get a plus and minus. I will have plus or minus 2. So notice that I will get two roots that are the same, but I will now be missing this root where x is equal to 0. So dividing means that I've lost this one very important root. Okay, so don't divide, factor. It is unfortunate though, for example, so let me go back to this example right here. I've done this exact same thing here. Now here, I wouldn't have actually noticed the difference because x equals 2 was not allowed in the first place, but there's no such restriction on this case, which means that I have to be really careful not to lose anything. So the message is, do not divide, but factor. Okay, moving on to our last two examples in this part. Let's take a look at this guy right here. So I do have square roots, but they are present in both sides, and they're both square roots of x. So let's move everything to one side and then see what happens. Let me say I'm going to move the square roots over to the left. So I'm going to subtract 2 root x from both sides. So here I'm going to then have root x minus 2 root x equals, and I'm going to move the number 3 from this side over to the right. So I'm going to add 3 to both sides. So I'm going to have 5 plus 3. And now I can combine similar terms. So notice that this root x, there's one of them, and then there's minus 2, also root x. So I can treat this as if I have an apple minus 2 apples, how many apples am I going to have? These are similar terms. So I'm going to have minus 1 root x, or simply minus root x. Okay, so don't be scared by the fact that it's root x. You still do similar terms the same way that you would done with any other variable. 5 plus 3 is, of course, 8. So I have that negative square root of x is 8. If I'd like to isolate x, then I'm going to move or multiply everything by -1, or move the negative sign over in this way by multiplying. So I have that root of x is -8. Well, I know for a fact that a square root that is implied to be positive can never give me a negative number, which means that this immediately produces no solutions. Okay, so I didn't have to go through and squaring and then checking for extraneous solutions that I would have gotten, because this simply will not work. In this last question here, I have a lot going on. I have several parts with x's appearing in everything. So this is somewhat reminiscent of this first question that we did in terms of having denominators, except for here the left-hand side has two things. So before we can do anything, I'm going to have to do common denominators on the left-hand side. Also note that just like in the first example on this page, right away I can think about what are some of the values of x that are not going to be allowed. None of the denominators are allowed to be 0, so I know right away that x cannot be 5 and x cannot be -5. So I cannot have plus or -5 as values of x in the solutions. Okay, so proceeding to take common denominators of these guys, I notice, of course, that x squared minus 25 is x plus 5, x minus 5, and the common denominators here will involve me multiplying exactly by those things. So the first fraction I have to divide and multiply by x plus 5, and the second fraction I have to divide and multiply by x minus 5. So putting everything together, what am I going to have? On top, I'm going to have x plus 5 from the first fraction, plus x minus 5 from the second fraction, and the common denominator will be x plus 5, x minus 5, or x squared minus 25 if I open up the brackets. Now this conveniently turns out to be the exact same denominator as the one on the right. So first I notice here that, for example, the 2 5s will cancel each other out. And so what I have on the left-hand side is actually 2x over x squared minus 25 equals 10 x squared minus 25. Okay? So notice that if the denominators are equal, then in order for my fractions to be the same, the numerators have to be equal to each other as well. So in my next step, I can simply proceed to say that 2x is equal to 10, which means, of course, that x is equal to 5. Now here, I know that I was not allowed to have x equals 5, and this is another way this is another one of these equations where we'll have to check for extraneous roots in order to make sure that we did not somehow introduce things that will make the denominator 0. Because x equals 5 will make this first denominator 0 as well as the one on the right-hand side. This, of course, then is an extraneous solution. And so overall, we have no solutions to our equation, not this one. Okay, so these are all the types of equations that are essential for calculus. Please take a look at the exercise at the end of the section, as well as web work assignment module 1D for more practice with all of this. This does take quite a bit of practice to get comfortable with, but you will get comfortable with these, trust me.